Hello and welcome to this lesson on synthesis of chloroalkanes. Let's just establish what these two words mean. First of all, chloroalkanes. You know that an alkane is just carbon and hydrogen, and like methane, for example. So methane we could simply draw like this, and that would be methane. And so a chloroalkane, like chloromethane, would just be when you substitute one or more of the hydrogens with a chlorine, and that would now be chloromethane. And you could do that with 1, 2, 3, or 4 of the hydrogens. Okay, so that's a chloroalkane. What about this word synthesis? Synthesis just means to create, in this context, chemicals. So this is a step by step process whereby chemicals are created. So it's quite important in the chemical industry how we actually create new molecules. And so this is our first look at like breaking down an overall reaction into several steps. Okay, so there's our two key words learned. What topics are we going to look at in this lesson? Well, we're going to have a look at the synthesis of chloromethane. And the 4 steps that are involved in that, 4 steps. Then we're going to have a look at CFCs. So you may have heard of CFCs, stands for chlorofluorocarbons. So we're going to understand what they are and also the impact that they have on the ozone layer. Or these days, the impact that they used to have on the ozone layer, because it's a problem that's largely been solved. So let's start to talk about the synthesis of chloromethane. And to start with, let's look at methane, for example, because I just want to establish that we can have different types of chloromethane. So that's methane, standard methane, CH4. But if we were to substitute one of these hydrogens with a chlorine, you would get chloromethane. If you were to do it with 2 of the hydrogens like that, you would have dichloromethane, and then trichloromethane, and then you would have tetrachloromethane. So they are the 4 chloromethanes that we're going to have a look at. And this type of reaction, when we make chloromethane, is a photochemical reaction. Let's write that down. Photochemical reaction, because it uses sunlight, and it uses radicals. It creates free radicals. Free radicals, which may be a new concept for you. So we'll have a look at that. Free radicals. So let's say we had a chlorine molecule. All right, so you've got chlorine atom, covalent bond, chlorine atom, and in that molecule you've got 2 electrons in that covalent bond, and then you might get some sunlight. Let's draw sunlight in red. So we got some sunlight radiation, and what happens is that that bond breaks. It's just the right, if that's ultraviolet radiation, it's just the right energy to break that bond. And so this electron returns to this chlorine atom, and that electron returns to the other chlorine atom. And so you end up with 2 chlorine atoms with their unpaired electrons. And so the unpaired electrons are drawn as a dot, so that you would have 2 free radicals like that. So a free radical is an atom or a molecule with an unpaired electron. And in chlorine's case, it's just the same as a chlorine atom. A chlorine atom is a chlorine free radical. But let's do methane as well. So if you had CH4 and you used a bit of sunlight to break this bond here, you would get CH, one of those electrons goes back to stay with the carbon, and you would get CH3 as before, but you would have an unpaired electron which we draw as a dot like that, and that would be a CH3 free radical. And they're very reactive, so free radicals are very reactive. Electrons don't like to be unpaired, and so that's what makes them very reactive. And this process of making chloromethane occurs in 4 steps. So we're going to look at it step by step, and the first step is called initiation, and that is the step that we sort of done at the top here. The initiation step is when we get the chlorine molecule splitting up, and this is how we're going to write it. We get a Cl2 molecule with ultraviolet light catalyzing this reaction from to give you the two chlorine atoms. And then after that's happened, you get to what's called propagation. And you can think of propagation as being like a chain reaction. Like a chain reaction, because the free radicals are used up and then recreated to go and create some more havoc. So let's have a look. So you've got a chlorine free radical from the first step, the initiation step, and that is going to come across a methane molecule, and the free radical decides that it doesn't want to be on its own. It's really going to have one of those hydrogens in the methane molecule, and so then what happens is you get a hydrogen leaving with its electron this time with the chlorine. So you get a hydrogen chloride molecule, and that leaves behind it the carbon and 3 hydrogens as they were before, but that electron in the covalent bond, stays unpaired with the CH3 molecular ion as a free radical. So you can see we've used up one free radical, the chlorine atom, and we've created the CH3 free radical again. And so that CH3 free radical, then let's just draw that like this. That's the CH3 radical, and that goes on to break up or react with another molecule, and so there's another chlorine molecule nearby, perhaps, and that is going to make another new molecule. It's going to take going to create this molecule here, that's chloromethane, and leave another free radical there. So you can see that the combination of these 2 steps means that you started off with a methane molecule and a chlorine molecule, and you ended up with a hydrogen chloride molecule and a chloromethane molecule. Your chlorine free radical is still there, but our CH3 free radical was created and destroyed. It should have a dot on it like that. And so that's the propagation step. And the next step is called substitutions. I'll write that down here because we're going to write a few of them here. So in the same way as we had this chlorine free radical reacting with a methane molecule and stealing one of its hydrogens, we could do exactly the same thing with our chloromethane molecule here and this chlorine free radical, in which case you would get another of the hydrogens substituted out, so you would still have 1 carbon, you would only have 2 hydrogens left, but you would have 2 chlorine atoms in there instead of the 1, and in the process you would get another hydrogen chloride molecule condensed out. So that could happen, and then you could do that again, because we've still got two hydrogens there that could possibly be substituted, because in this process you're going to recreate your chlorine-free radical, and so that molecule there could react with our chlorine-free radical and make another product. So you would get one chlorine, one hydrogen, and one carbon, one hydrogen, and 3 chlorines. So that's trichloromethane, plus another hydrogen chloride molecule, and you would recreate another chlorine-free radical in the same step as this second step here. And the last step would be that if our free radical and our trichloromethane reacted together, and then you would get your tetrachloromethane, like so, and the free radical and the hydrogen chloride. And so you can see that you would get 4 products all mixed up together. You would get chloromethane, you would get dichloromethane, you get trichloromethane, and you get tetrachloromethane. And lastly, our fourth step is called termination. It's the last step. So we're going to do that in this space here. Termination is our last step, and termination happens when either you run out of methane, or the free radicals react with each other and terminate them. So let's write down our free radicals. We've got chlorine free radicals in this case, and we've got CH3 free radicals. And if one of those meets, one of the chlorine free radicals meets a CH3 free radical, then you're going to get the CH3 Cl, the chloromethane. But if these two react directly together, then you're not going to get another free radical, and so those free radicals have cancelled each other out. So that's one termination reaction. There are 3 altogether, because you could actually have 2 CH3 free radicals bumping into each other, and they would give you C2H6, an alkane, and that is unreactive and wouldn't take any further part in the reaction, and those 2 free radicals will have cancelled each other out. And the other combination of free radicals that you could get is a chlorine free radical reacting with another chlorine free radical, giving you a chlorine molecule. And so that's the termination step that will happen. So that's how we make chloromethane, and when that's made, we're going to get a mixture of those 4 chloromethanes: chloromethane, dichloromethane, trichloromethane, and tetrachloromethane. So we're moving on to chlorofluorocarbons now. So this lesson started off being about chloroalkanes, and here we are introducing fluorine into the situation. And a chlorofluorocarbon is something like this. So you might have a carbon in the middle, and you might have 3 chlorines. So 3 chlorines around the carbon and 1 fluorine. And so this would be trichloromethane. Another example of a chlorofluorocarbon would be, say, the other way around. You would have a carbon and 3 fluorines surrounding it, and 1 chlorine, and so this would be chlorotrifluoromethane. And of course you could have difluoromethane as well. So, and also you could have more than 1 carbon in there. So there's lots of chlorofluorocarbons. We've got 2 examples there, and the reason they're interesting is that they used to be destroying the ozone layer. Unless we continue to be careful, they would finish the job, and we'd all get fried by the sun's ultraviolet radiation. So what we're going to do is have a look at the process by which chlorofluorocarbons destroy the ozone layer. But first, let's make sure you know what ozone is. Ozone is an O3 molecule. So as you know, in air, pretty much all of the molecules, the oxygen molecules, are O2 molecules. Well, there is another structure of oxygen that is O3, and that's called ozone. And ozone finds itself up in the upper atmosphere and forms a layer in the upper atmosphere that I'm just sort of denoting with that red squiggly line there. And that's useful because the sun's rays that come to the Earth, particularly the ultraviolet rays, are somewhat absorbed, and so fewer of the ultraviolet rays make it down to the surface of the planet, and that's good because otherwise we'd get burnt. And what was happening was that chlorofluorocarbons that were present in fridges and aerosol cans, they were finding their way to the ozone layer and reacting with ozone. And we're going to study that reaction. So firstly, to have an ozone layer, you need some ozone. And ozone starts off with oxygen, right? So an O2 molecule has made its way to the upper atmosphere, where it is going to interact with a lot more ultraviolet rays. And so you're going to get the, so I'm going to call this HV. HV is a bit from physics. H is Planck's constant, and F is the frequency of the ultraviolet rays. But basically it just means the energy from ultraviolet rays. So, so an oxygen molecule receives this energy from ultraviolet that we've called HV and turns itself into two oxygen free radicals, like so, in the same way as chlorine did as well. And then those free radicals can themselves react with other oxygen molecules that have made their way up to the upper atmosphere. So they're going to collide, and you're going to make an O3 molecule, and that's how we get ozone. So now we've created ozone, and we like that because it saves us from the ultraviolet rays. Now we're going to have a look at how ozone is destroyed. So step two would be how we get, let's call it the involvement of the CFC. So let's draw ourselves a chlorofluorocarbon. Let's do trichlorofluorocarbon. So we've got one carbon, we've got three chlorines, and we've got a fluorine. That's our CFC. And in the same way, with the ultraviolet radiation, the energy of which we've called HV, we're going to split that molecule up and create two free radicals. So we're going to get a Cl2F free radical, and we're going to get a chlorine free radical, like so. So now we've got two free radicals, and they're going to cause some havoc. So we're going to write the havoc in the third step. So let's take the third step involves taking this nice friendly ozone layer, or at least it's friendly when it's up in the upper atmosphere, and this nasty chlorine free radical. So we've got some ozone, and we've got a chlorine free radical, like so, and the chlorine free radical is going to attack the ozone molecule and break it down into an oxygen molecule and leave us with another CLO free radical, like so. And that CLO free radical doesn't just wander off and mind its own business. No, it attacks another ozone molecule. So we've got a CLO free radical, happens to bump into another ozone molecule, and creates two oxygen molecules, and in the process recreates the original, well, not the exact original, but a chlorine-free radical, just like we had in the first step of this reaction. So this chlorine-free radical then makes its way around and to here and reacts with another ozone molecule in another first step reaction like that, and on and on and on. So just by creating one chlorine-free radical, they go on to destroy lots of different ozone molecules because they're recreated. So the overall reaction, is like this. So we started off with ozone, and we created oxygen with the chlorine-free radical as the catalyst, and just to balance that we're going to need 2 of those and 3 of those. And that's the overall reaction, and that's how chlorofluorocarbons destroy the ozone layer. So we move on now to talk about to summarize the environmental problems of CFCs, and we can see we've got a picture of a fire extinguisher here, a fridge, and a aerosol propellant, and the pictures are there because these are the 3 most common examples of where CFCs were used. And so CFCs would be evolved from these 3 products, eventually find their way into the upper atmosphere and do create havoc with the ozone layer. And so they've been replaced largely. So they've been replaced. CFCs have been replaced, and they've been replaced by a temporary solution so far. So one temporary solution is hydrogen fluorochlorocarbons. Hydrogen, so that's hydrogen fluorochlorocarbons. So as long as you don't have the carbon surrounded by just fluorine and chlorine, if you introduce a hydrogen back into the molecule, then that stabilizes it a bit. It doesn't break down in ultraviolet and thereby create the free radicals. So that's one way you can do it, and the other replacement is hydrogen fluorocarbon. So you haven't got any chlorine in there at all, so you've got hydrogen fluorocarbons. So they're less dangerous, all right. So I just put because less dangerous. But also, so that's one way that we're solving the CFC ozone problem. The other way is to instead of using CFCs in foam products, we're using CO2. So it's carbon dioxide used instead of CFCs in foamed polymers. You know, like the packaging polymers you might buy a laptop or some sort of precious item in. And your aerosol cans, whereby the propellant used to be CFCs, nitrogen is now usually the propellant. Propellant just being the gas that propels the product. Let's say it's a deodorant. It propels the deodorant molecules from the can onto your skin. And some of the aerosols are also pump action now as well, which clearly is going to be safer. So there's 2 or 3 ways of solving the environmental problems of CFCs, and that brings us to the end of this lesson. So I hope that's been clear for you.